Tattooing dates at least as far back as the Bronze Age. A 5,000-year-old body found in a European glacier had several tattoos on his skin. Archaeologists have even uncovered what they believe are Stone Age tattooing instruments, sharp bone needles and clay discs containing mineral pigments. Walk into a tattoo parlor and the vast selection of elaborate designs will astound you. Once you make your choice, the tattoo artist traces the image. Next, he places the traced image on carbon paper and retraces the lines. This creates a carbon outline of the tattoo on the reverse side. The artist will use this blueprint, as it's called, as his guide. He cleans the customer's skin, then firmly presses on the blueprint. The carbon image transfers easily because the skin is damp. Now it's time to construct the needles. Most tattoos require 2 needles, one to make the outline of the image, the other to shade and color it in. Each needle is made up of as many as 20 smaller needles. The artist aligns these small needles in a jig, then solders them together onto one end of a steel rod. There's an eye on the other end. The number of small needles in a needle depends on the tattoo design, how thick its lines are, how big its colored areas are. The finished needles go into an autoclave to be sterilized. That takes 20 minutes at precisely 170 degrees Celsius. The tattoo artist uses that time to assemble the tattoo gun. After cleaning the frame with rubbing alcohol, he installs the motor called the coil. When an electric current runs through the coil, it oscillates the needle at up to 50 times per second. Once the 2 needles are sterilized, he takes the one for outlining, called the liner, and slides it into the tattoo gun. He hooks the eye on the other end onto the spring. As the spring moves back and forth, it moves the needle up and down. The tattoo artist stops and starts it with a foot pedal, like a sewing machine. Time to tattoo. He turns on the power supply to 10 volts and dabs the needle in the ink cap. The gun sucks up the ink. Some petroleum jelly on the skin helps the needle glide more easily. He begins by tracing the lines of the blueprint. The needle punctures the skin at a rate of up to 3,000 times per minute, injecting microparticles of ink which intermingle with the cells of the dermis, the skin's second layer. The artist continually wipes away the excess ink to keep his work area clean. After finishing the outline, he reapplies petroleum jelly. This seals the pores of the skin and prevents bleeding. Then he changes to the other needle and begins shading and coloring the image with a back and forth movement. He applies one color at a time, overlapping them to ensure thorough and even coverage. The needle can penetrate from 1 to 4 millimeters, and a good tattoo artist knows just how deep to go to create the different parts of the image. For example, he has to inject the outline the deepest, but going too deep can tear the skin and cause excessive pain and bleeding. But not going deep enough misses the dermis and leaves marks after healing. The cells of the dermis are remarkably stable, so tattoos last a lifetime. This tattoo has taken approximately 45 minutes to do from start to finish. The area will dry and scab over. Then, the scab will fall off, and this body art will be ready for exhibition. We take well-lit streets for granted, but there was a time when venturing out at night meant traveling in complete darkness. In 1814, the first gas lights lit up the streets of London, England. The first electric streetlights illuminated a public square in Cleveland, in the United States, in 1879. These streetlight poles are made of what's called composite, a combination of fiberglass and epoxy resin. Epoxy resin is a gooey liquid plastic mixed with a hardener. The factory constructs each pole on a mandrel, a long tapered metal cylinder. Workers first lubricate the surface. Then they take what's called fiberglass filament, a string composed of 2,200 tiny fiberglass strands. They'll wind dozens of filaments around the mandrel to create the pole. But first, the filaments go through a bath of epoxy resin. This resin is moldable, and once it's heat-cured, maintains its shape. Once the filaments come out of the bath, a machine called a filament winder wraps them around the rotating mandrel. The speed of rotation in relation to the speed of the winder is critical because it dictates the angle of the fibers. The lower the angle, the more that part of the pole will be able to withstand the wind and provide constant, stable lighting. When a pole bends in the wind, the light appears to flicker. The number of filament layers depends on the design of each specific pole, and that's determined by a couple of factors. First, the type of light fixture the pole will hold. The bigger the fixture, the stiffer the pole has to be. The other factor is wind. The windier the location, the stronger the pole has to be. Once the winding's done, the mandrel moves on to the curing station. They pump pressurized steam into the hollow inside of the mandrel. The heat kickstarts the hardener in the epoxy resin. This solidifies the resin and cures it. The mandrel rotates so that the pole cures evenly. Curing time depends on the length of the pole and how many filaments it's made of. To help extract the pole, they pump cold water through the mandrel. This makes the steel mandrel contract, loosening the pole. Remember how workers lubricated the surface of the mandrel before winding the filaments? Because of that, the pole just slides off. The pole now moves on to the finishing stages. First, an automated sander works the surface. The customer can order from a choice of surface textures, from smooth to rough. Sanding takes just a few minutes. Now a saw makes a neat cut at the top of the pole where the metal tenon will go. A tenon is the component that'll hold the light fixture to the pole. This particular model has an arched mounting arm. The composite has cooled a bit since curing, so they reheat it to make it flexible. After a bending machine makes the curve, they spray cold water inside to cool the material. This registers the curve in the resin's memory, setting the bent shape. Now they cut out the hand hole, the opening through which the electrician will connect the underground wire to the fixture wiring. Workers then spray the pole with urethane paint. The paint acts like sunscreen, protecting the composite from damaging ultraviolet rays. This grommet hole will connect to the underground pipe that contains the electrical wires. After installing a cover over the handhole, it's time to assemble the parts. The underground pipe to the pole, and the pole to the tenon and light fixture.
When some innovative caveman invented the bow and arrow, it was a huge breakthrough. The discovery turned the Homo sapien into an efficient hunter-gatherer. These days, archery has made a comeback in the hunting community, and it's even been reclassified as an Olympic sport. So you could say the caveman's invention is still right on the mark. Today's bows are definitely not primitive devices. Crafted with calculated precision, they make it easier for you to take your best shot, and the caveman would have been very impressed. To make a longbow, a craftsman cuts 6 strips of cherry wood, a little more than ½ centimeter thick, using a bandsaw. Then with a belt sander, he repeatedly thins the wood strips on both sides, tapering the ends a little each time. The tapering gives the wood some flexibility, which the bow will need to launch arrows into the air. With his bandsaw, he now carves a handle from a piece of wood. Next, he brushes super adhesive glue onto fiberglass strips and the tapered strips of cherry wood. He works swiftly because the glue will start to dry in less than an hour. Now he layers the strips. The fiberglass strips buttress the 6 glued wood strips on either end. This process is called lamination. Next, he glues the wood handle to the fiberglass and wood lamination. And he tops it with a piece of masking tape to protect it from scratches and glue smudges during the next steps. Now the laminates get the squeeze. He places them on a curved plywood shape called a bow form. He positions a steel heat strip, a rubber hose, and another plywood form on top of the laminates. He clamps it all together, then inflates the rubber hose with an air compressor. The pressure from the hose combined with the heat from the metal strip mold the wood to the bow shape as the glue sets. 1 hour later, he removes the laminates, nicely pressed and glued into more bow-like curves. Now he draws the bow form onto the newly curved lamination, following a template made of fiberglass. With his bandsaw, he cuts the wood along the lines he's just drawn. He cuts an arrow shelf. That's the notch for the arrow to rest as the archer aims. Then he trims the handle, making it a little wider at the center for comfort. Next, using a coarse-toothed file, he hollows out little grooves in the upper and lower limbs of the bow. They're called string nocks, and the string will loop around them. To strengthen the tips, he glues little pieces of fiberglass and moose horn over them and the freshly filed nocks. He clamps it in a vice grip to set. When it's dry, he files through the horn and fiberglass to bring back the nock groove. He smooths it with sandpaper. Now he glues another piece of wood over the handle to improve the look and feel of it. He clamps it together while the glue dries, and 3 hours later, he sands it. Next, he wraps the handle in a piece of leather and stitches it together with nylon thread called artificial sinew. Many years ago, they used the tendons of an animal for thread. The leather will make the bow easier to grip. With a gel pen, he writes a serial number on the back of the bow, along with the draw weight. This bow will hold about 20 kilograms of pressure in check when it's drawn. This is a Flemish string jig, a wood fixture with posts on it. He loops nylon string around the posts. This is how he measures the string. It's always 4 inches shorter than the bow. He cuts it with a utility knife, then rolls wax onto it to make it easier to work with. He measures some string. Then he twists 16 strands of nylon, 8 black and 8 white, into a braid with loops on the ends. He hooks the string on the nocks, and it's time for target practice. As he bends the bow, energy is stored. He releases it, and the energy propels the pointed projectile. That apple didn't have a chance.
The violin developed in the 1500s, evolving from a series of guitar-like instruments that musicians played with a bow. While the violin is best known for classical music and gypsy music, today you hear it in pop, country, bluegrass, and even jazz. First, they cut a piece of maple, then split it in half to expose the grain in mirror image. They melt down glue flakes made from animal hide, then bond the pieces together. Violin makers use only glue, never nails or screws. These pieces of wood will form the back of the violin. After 4 hours, the glue is dry and they can remove the clamps. Using a small plane, they even out the surface. Then they trace the violin's shape and cut it out. They shave the surface, sculpting a downward slope from the middle, using an even smaller plane. Then they carve a groove along the circumference. After dabbing it with glue, they insert what's known as purfling, a reinforcement made from a thin strip of hardwood, usually maple. Finally, they carve the reverse side to the right form and thickness. Next, they make the sides of the violin, known as the ribs. First, they soak thin strips of maple or sycamore and press them against a heated bending iron to curve them. Then they glue the strips around a form, connecting them at the top and bottom and at the corners with small blocks of wood. They clamp everything together and let the glue dry for 4 hours. Next, they glue thin strips of wood, called counter ribs, onto the edge of the ribs. This enlarges the surface so that it's easier to glue the ribs and the back together. They make the violin's front, or belly, from a solid piece of spruce. To the underside, they glue a spruce support bar called the bass bar. Sound escapes through the 2 curved slots called F-holes. They cut out and carve the violin's neck and scrolled head from a piece of maple. Then they glue it to the body. They sculpt the fingerboard from ebony, a hard wood that's durable enough to withstand centuries of violinists' fingering. Using a tool called a peg hole reamer, they make holes for the ebony or rosewood pegs around which the strings are wound. They coat the wood with 4 or 5 coats of varnish, depending on the color, then polish it with several coats of oil over several days until the finish is shiny and silky smooth. Next, they insert the sound post. This little pine cylinder conducts sound and supports the belly against bowing pressure, so it's critical to position it in precisely the right spot between the belly and the back. It's not glued, but rather wedged into place. The bridge isn't glued either. It's held in place by the pressure of the 4 strings, which they feed through the ebony tailpiece and wind onto the pegs. The bridge has little notches in which the strings sit. The violin is finished. They make the bow from horsehair and a high-quality Brazilian wood called Pernambuco. They bind the hairs at one end with a strong sewing thread, then burn them and seal them with wax to prevent fraying. This end goes into the frog, the wooden box at the bottom or heel of the bow. They cover the frog with a mother-of-pearl lining, then slip on a ring made of nickel, silver, or gold to prevent the hairs from tangling. Next comes the screw that controls the tension of the hairs. They comb the hairs to make them parallel, then insert them into the tip of the bow, known as the head. They tighten the screw until the hairs are taut. Finally, they rub on rosin, a sticky pine tree resin that keeps the bow from slipping off the strings.